Speaker who is going to be Dario Billi. Dario, it is a pleasure for us for attending to your presentation. Thanks.
Okay. Good morning to everyone. I'm Dario Billi from the University of Pisa and Florence, and today I will introduce to you my research activity that focuses to capture and retain information of reflectivity, transparency, homogeneous texture, non-Lambertian surfaces regarding a large number of artifacts, for example, of the cultural heritage. And to use, in recent years, much research has been dwelling on these problems, trying to use the computer vision and artificial intelligence integrated with the standard photogrammetry. In 2023, it has been developed the Gaussian splatting method regarding the computer vision. But what is a Gaussian splatting? It is a differentiable rasterization techniques that use 3D Gaussians that are ellipsoids in the space to reconstruct scenes in order to create novel view synthesis and real-time rendering. In the standard process, the triangle rasterization is not differentiable. It only includes discrete decisions without the possibility to use the integral volume density that allow to parameterize important features, as I said before. Each 3D Gaussian is parameterized by the mean, that can be interpreted as the position, the covariance, that is an isotropic covariance, that indicate how much is stretched or resized the Gaussian, the opacity, that is a sigmoid function applied to map the parameter to the interval 0 to 1, that indicate how much transparent is it, and the parameter colors that are RGB and the spherical harmonics that indicate the reflection. In fact, the spherical harmonics are special functions defined that are able to calculate the ability of the object to reflect and to create specularity. The Gaussian splatting methodology starts from the generation of sparse point cloud from structure for motion, normally by default call-map. After the second step, they regard the initialization, where the points are converted in 3D Gaussians, starting as sphere at the first attempts. In the third point, there is the projection and the rasterization that regards the projection of 3D Gaussians in 3D Gaussians parallel to each frame image, creating the rendered images thanks to the rasterizer. In the fourth step, there is the comparison between the generated and rendered images and the original one, the ground truth, computing a loss function to adjust all the Gaussian values. In the 5th point, there is the adaptive density control, that is an automated densification and pruning of the 3D Gaussians. There is, after an iteration between the 5th point and the 3rd point, in order to, until the rasterized images are really, really close to the original images. As output from this methodology, we have a real-time rendering on viewer, plus a point cloud for each iteration that by default are set by 7,000 to 30,000 steps. In the Gaussian splatting, we want just to focus even in the adaptive density control. Just to make example, if a Gaussian is really, really large, to define a specific detail in that part, it is divided. Or if it is small and needs still to define better a fine detail, it is cloned. Or if the alpha of the Gaussian is really, really low, so near to be transparent, it is removed. In the first studies that we concentrated, we focused in two most important settings, available, of course, of the Gaussian splatting, that is on Windows and Linux, using the Anaconda prompt. There are many, many settings, but we decided in these first attempts to focus in resolution and iteration. The resolution, if it is not set, and input image width exceeds more than 1,600 pixels, the inputs are automatically rescaled to this target, while the iteration are the number of total iteration steps that are 30,000 by default. In these first attempts, we decided to use this first pilot case study that regards a plastic bottle inside a model, with 80-90 images, and these are the first 3D Gaussians output that came out. The free Gaussian splatting on the left cloud, and the real-time rendering with the splat, and as you saw before, the Gaussians. We want just even to understand how it works, the iteration and the resolution. We decided, in fact, to left all the default to settings all by default and changing only the number of iteration. And as we can see, only the time, of course, the time processing is varying, but the number of point cloud after 30,000 steps is more near, is exactly, not exactly the same, but is really, really near to the second time processing and the second iteration. This it means that the number of iteration are important just to best fit and set the Gaussian, the adjustment of the Gaussian inside the model. While if we just left all by default and we change only the setting of the resolution, we can see that the number of points is varying a lot, and of course the time processing too. In the first attempt, we decided even to create an hybrid mesh from Cloud Compare. And as you can see here are these three methods that compare together. And as we can see, the 3D Gaussian plus Cloud Compare method is not so much performed like MetaShape in the geometry, but if we just focus on the bottles, on the plastic bottle, and we compare it with the ground truth, we can see that there are better geometric completeness of the bottle, but in terms of disadvantages, we don't have a low control of the normal estimation parameter, and there is not possible to extract texture and MTL files. In 2024, it has been developed an important plugin for 3D Gaussians that create a high-quality mesh. The steps, of course, are many settings too in this prompt, are the first, that is an adjustment that brings the Gaussians that are unconstrained in the 3D Gaussian model that is the input, of course, of the SuGaR method, to align well with the object surfaces through the SDF or the density function based on the depth maps obtained from the 3DGS model. At the second step, the extraction of a coarse mesh using the Poisson reconstruction. At the third step, an optional joint refinement of mesh and 3D Gaussian rendering. At the first step, the optimization and the final output extractions. So the process, by doing various tests and degrees of iteration, is this one, the result. Now here there is a first test comparison between the improvement with the SuGaR. This one is another one. Now I'm just showing some test results that we done in these first attempts. Of course, between MetaShape and 3D Gaussian splatting, plus SuGaR. This is an old data set to compare and to just highlight the difference between the texturized mesh on NERF, for example, and the photogrammetry. This one is another old data set. And so, with the future works we want, and the goals to achieve, we want to continue to research these new methodologies that further can improve the results. One most important point that we want to reach is to consolidate a methodology that not only includes qualitative analysis, but also quantitative and metric analysis, and also to combine this technology with the standard post-production methods. This is the bibliography references. Thank you for your attention.
Thank you very much, Dario. Is there any question for Dario? Probably no. I just have a curiosity. So, this kind of, let's say, technology based on AI is becoming more and more popular during the last years. And it's also quite impressive to see the ability of reconstructing certain quite hard object to be reconstructed with standard photogrammetric tools, such in your example, a transparent bottle. However, I was wondering, in particular for what concerns the third bullet of your conclusions, if you already have some kind of at least basic results on the quantitative evaluation of the methods.
Metrics.
So if you have made some kind of comparisons for what concerns the geometry, actually. So you mostly show us something related to the coverage of, to the completeness of the reconstruction of the object, but I was wondering about the geometry.
Yes. This is the first goal that we want to achieve immediately, because we need, of course, to understand better even the metrics parameters, but still we didn't achieve it because it was so near to process all these models, and still we need to see better all the settings, to adjust, and of course to export in the metrics, as we done it for example for nerves and narrow radiance fields.
Thank you very much, Dario. So